Welcome to this next video in the playlist on group theory. In this video, what we're going to study is groups of order PQ, where P and Q are both prime numbers, different prime numbers. Indeed, the previous video in this playlist on group theory was on groups of order P squared, where you just had a single prime number squared. Here we are going to assume that we have two different primes in the prime factorization of the order of the group. Okay, so we've got some finite group then, which has order P times Q. Okay, and we might as well assume that P is the smaller of the two. One of them has to be smaller than the other, so let's just assume that P is the smaller one and Q is the larger one. So we're giving P, we're giving the name we're giving to the smaller prime in the prime factorization of the order is P, and the name we're giving to the larger prime in the prime factorization is Q. Okay, so we're talking about finite groups which have this very simple order, i.e. If you get the order of them and take the prime factorization of their order, you get these two primes, one prime called P and the other prime called Q, and they're both to the power of 1 in their prime factorization. Okay, so before we get into the theory then of these groups of order PQ, let's just see some examples of orders that groups could have which would actually satisfy this. Okay, so some examples then. If we had a finite group of order 6, that would be an example, because 6 is 2 times 3. 2 is the smaller prime, so it's taking the place of P, and in this case Q would be equal to 3, the larger prime. Another example would be 10, that's 2 times 5, so P is equal to 2, Q is equal to 5 in that case. 14 is another example, 2 times 7, P is equal to 2, Q is equal to 7. Another important example is 15, which would be 3 times 5, so P would be equal to 3 and Q would be equal to 5. Okay, so there's some examples. So this video is going to be on groups of these sorts of orders, where if you take the order and you factorize it into its prime factorization, you just have two primes that are different appearing in that prime factorization, and they're each to the power of 1. Okay, right. So let's begin then with the theorems that I'm going to give you in this video concerning these groups of order PQ. Okay, so the theorems that we are going to study, they're all about using the Seelof theorems to unravel the structure of these groups. Okay, so if you're not familiar with the Seelof theorems, you do need to go and watch the video that I have on the Seelof theorems, in which we state and prove the Seelof theorems. This is going to be the first example video in the playlist on group theory where we're actually going to apply the Seelof theorems to understand groups. Okay, so, but I'm not going to go over the Seelof theorems again, because they take quite a long time to actually prove. Okay, so, assuming then now that we are all familiar with the Seelof theorems, let's now actually start with the theorems concerning these groups of order PQ. Okay, so, Theorem 1 then. Theorem 1 concerns an arbitrary group of order PQ, okay, and the conclusion that we're going to make as Theorem 1 is going to be that there is only one Seelof Q subgroup of G. Okay, now firstly actually, let me just talk to you about what we're actually going to be doing. We're going to be talking a lot about subgroups initially of the group of order PQ. Now, by Lagrange's theorem, there are not that many possibilities for the order of subgroups of these groups of order PQ. Because remember, by Lagrange's theorem, any subgroup of this group is going to have order which divides the order of the group, and there aren't that many numbers which divide the order of the group. 1 divides the order of the group, P divides the order of the group, Q divides the order of the group, and PQ divides the order of the group. Now, of course, the only subgroup of size 1 is the trivial subgroup, which I'll denote 1, and the only subgroup of size PQ is the improper subgroup, i.e. the entire group capital G. So what we're now going to be trying to understand is what about the in-between ones here? Groups of order P and groups of order Q. Okay, or subgroups of order P and subgroups of order Q. Okay, so here's the question now. Now, Seelof's first theorem tells us that there must exist subgroups of size q and subgroups of size p, because after all, if we take the prime factorization of the order of the group, p is one of the primes that appears and the highest power is p to the power of 1, and q is another prime that appears and its highest power is q to the 1. And of course Seelov's first theorem tells us about the existence of subgroups of order each of the primes that appears in the prime factorization to the highest power it appears. Okay, and in that case there must exist a subgroup of size p and a subgroup of size q, at least one in each case for this group of order pq. Okay, so indeed the subgroups of size p are going to be the Seelov p subgroups of this group, and the subgroups of size q are going to be the Seelov q subgroups of this group. Okay, so we are now going to study those Seelov p subgroups and Seelov q subgroups then. So theorem 1 is that there is only one Seelov q subgroup. So theorem 1 is that the number of Seelov q subgroups, denoted nq, which is just the order of the set of all Seelov q subgroups, is equal to 1. There is only one subgroup in any group of order pq of size the larger prime. Remember, q is distinguished from p because it's the larger of the two. Okay, there's only one Seelov q subgroup, okay, in this group of order pq. Now what does that then imply? Well, that implies that if you have this Seelov q subgroup, so let's say q, capital Q, is now going to represent this Seelov q subgroup, so it is an element of the set of all Seelov q subgroups of G, which of course we know has order 1. So let's say now that q is this subgroup of size little q here, okay, then you can instantly conclude that q is normal within G, okay? In fact, you can even conclude the stronger condition that it's characteristic in G. Okay, now why can you do this? Well, we know that it's the only subgroup of this group here, capital G, of order Q. Now, that tells us that it's going to have to be characteristic in G because, remember, the definition of characteristic means that whatever automorphism you take of the group capital G, Q is fixed by that automorphism. Now an automorphism must map a subgroup onto another subgroup of that same size. If there's only one subgroup of that size, then it must just map it onto itself, and therefore Q would be characteristic in G. Now, of course, whenever you've got a subgroup that's characteristic in G, it's also normal in G. Normal in G is just a weaker version of characteristic in G. It means that if you conjugate Q by any element of the group, which is effectively an inner automorphism of G, okay, then Q must be fixed. And again, the same argument applies here. Because when you conjugate Q by any element of the group, it must be mapped onto another subgroup of the same order. If there's only one subgroup of that order, then it must just be mapped onto itself, and hence it must be normal inside the group capital G. Okay, so this Seelov q subgroup, which is the only one, is then going to be normal and the even stronger version characteristic in G. However, these two things are absolutely identical to one another if we're talking about a Seelov q subgroup, and let me explain the reason. Usually, being normal in a group does not imply that you are characteristic in a group. Okay, this one is the stronger condition. This one says that you're fixed by all inner automorphisms, by any automorphism that is of the form conjugation by an element of the group, whereas this one says that you're fixed by all automorphisms, even the automorphisms that are not inner automorphisms. Okay, so usually saying this is not good enough to say this. However, if you know also that this is a Seelov subgroup, then it is good enough to be able to conclude that it's characteristic in G. And the reason is that all Seelov subgroups are conjugate to one another by the second Seelov theorem. Okay, so if this Seelov subgroup is normal inside the group, then you can instantly conclude that it must be the only Seelov q subgroup. Or rather, let's generalize this, just say Seelov subgroup. Okay, so the instant you have that a Seelov subgroup is normal in a group, you can instantly say, and this goes beyond what we're just talking about here, this is a more general point actually. Okay, if you've got a Seelov subgroup that is normal, you can instantly conclude it's characteristic, and the reason is that all Seelov subgroups are conjugate to one another. So if it's normal, that implies there's only one Seelov q subgroup, or, sorry, I just said q again. There's only one Seelov subgroup of that pertaining to that prime. Okay, because otherwise it wouldn't be normal. If you conjugated it by something, you'd be able to find one of the other ones. Okay, and therefore, if there's only one of them, you can conclude that it must be characteristic in the group capital G. So in fact, these two things are equivalent when we're talking about seed-off subgroups. So often people don't bother talking about a seed-off subgroup being characteristic in G. If you've got a normal seed-off subgroup, then it's understood that that's going to be characteristic in G. So from now on, we won't mention this. Okay, it will be implicitly understood that yes, it is characteristic in G if it's a normal seed-off subgroup, but we'll just refer to it as a normal seed-off subgroup and understand that it's characteristic in G. Okay, so occasionally I will obviously mention this and point it out if it's incredibly relevant, but often people just say it's a normal seed-off subgroup and then people understand that it will imply that it's characteristic in G. Okay, right, Theorem 1 then is that there is only one seed-off Q subgroup, and if that is true, then this single seed-off Q subgroup is indeed going to be a normal seed-off Q subgroup and therefore also characteristic. Okay, so how can I prove this? Well, it's a very simple proof. We're just going to use the third seed-off theorem. So here comes the proof here. Okay, right, so what does the third seed-off theorem tell us? Well, the third seed-off theorem tells us conditions that the number of seed-off subgroups must obey. Okay, so the third seed-off theorem firstly tells us that the number of seed-off Q subgroups must divide, must divide the portion of the order of the original group that is left over after you get rid of the highest power that Q appears to. So Q only appears to 1, so get rid of Q there, and the bit that's left over is just P. Okay, so NQ must divide P. Okay, it also tells us that NQ must be congruent to 1 modulo P, i.e. it must be equal to 1 plus a multiple of Q, where K is greater than or equal to 0 here. Okay, so those are the two things that I know from the third seed-off theorem. Now, I claim that I can actually get some very useful information from this, and this is a really nice example of actually being able to use the third seed-off theorem to do something, because when you learn the third seed-off theorem, you kind of, well, when at least I kind of felt, what's the point of these sort of cryptic messages? Okay, I mean, you know, you'd like a beautiful formula for the number of seed-off subgroups, and the third seed-off theorem doesn't give you that. It seems to give you these really cryptic messages that it will divide what's left over of the order of the group once you've got rid of the highest power of the prime that you're talking about. Okay, and also that it'll be congruent to 1 modulo the prime that you're talking about. Okay, but here's an example of where you can actually get some very useful information, a precise answer basically, out of the third seed-off theorem in a context of a specific group of a specific order. Okay, right, so groups of order PQ, we can actually get some information out here. Okay, and the reason is that I claim K can only equal 0 here, because if K is anything greater than 0, so if K is equal to 1 for instance, NQ will end up being 1 plus Q. 1 plus Q cannot possibly divide P, because Q, remember, we are assuming is the bigger prime, it's bigger than P. Okay, so 1 plus Q is certainly bigger than P, and it therefore cannot possibly divide P, and the same is true for any higher K. If you make K even bigger, you just end up with a bigger number, then that's not going to be able to divide P. So the only possibility here is that NQ is equal to 1. Okay, so because Q is the larger prime by our initial assumption, one of the primes had to be bigger, and we called that one the Q1, I'm saying that we can only have one seed-off subgroup pertaining to this larger prime. NQ must equal 1, so there's only one subgroup in your group of order PQ of order Q. Okay, and there's the proof. Okay, so now I'll fill in this little chart here. We've only got one subgroup of order the larger prime in our group of order PQ. Okay, so that's very nice. That's extremely simple. It's following the really simple pattern. So now all we need to investigate is subgroups of order P. And here's where it gets slightly more complicated. Okay, it would be lovely if I could just now tell you that for all groups of order PQ that there was only one subgroup of size P. That would be absolutely lovely. That would complete this with full simplicity. However, that's not true in the general case where you've got a group of order PQ. However, it is true if we add an additional constraint on. Again, we are now, for the rest of this video, just going to study groups of order PQ when we have this when we have this additional constraint. Okay, you can study groups of order PQ, and you can say a lot more about groups of order PQ where you don't have this additional constraint. However, you need more advanced group theory to do that than we have currently. Okay, so I'm not going to do that in this video. Okay, I will probably make another video down the line again on groups of order PQ where we will finish this job, okay, and do it where this additional constraint isn't there, but right now all we can do it with is with this additional constraint. Okay, so now theorem 2, we're going to limit our attention down now to groups of order PQ where there is an additional constraint. So our group is still going to have order PQ, okay, but now we're going to insist that P, that the smaller prime, does not divide the larger prime minus 1. Okay, so we're still assuming that P is the smaller prime. Okay, so there's our additional constraint, and this rules quite a lot of the examples out now. Okay, so if I go back to my examples, we had groups of order 6 were of this form. That's 2 times 3. This doesn't obey this condition because the smaller prime is 2, the larger prime is 3, so 3 minus 1 is 2, so 2 does divide the larger prime minus 1. Okay, so 6 would not satisfy this condition. 10 wouldn't either because it's still 2 times 5. So when you take 1 off the large one, it will go down to 4, which is a multiple of 2. And again, the problem is the same with 14 because we've got 2 in there. So the other prime, when you take 1 off that, because the other prime is always going to be odd, when you take 1 off that, you'll get even, and therefore 2 will be a divisor of that. Okay, so that won't satisfy it. But then 15, we suddenly strike gold. Excellent. Look at this. 3 times 5. When you take 1 off the larger prime, you go down to 4. 3 does not divide 4. 4 is not a multiple of 3. So 15 is your key example here of a group that actually does obey this condition. Okay, right. So here's an example. To give you another example, to add a few more in, another example would be 33. Okay, because here, of course, you've got 3 times 11. Okay, 11 is the larger prime. Take away 1, you'll get 10, and 3 doesn't divide 10. So there's another example of a group that does satisfy this condition. So I'll repeat again, from this moment on, we're just going to be studying groups of order PQ that obey this additional condition, because these are incredibly simple now, and we can conclude a beautiful ending. Okay, whereas if you don't have this conclusion, it's more complicated. Not that much more complicated, but proving the results for those other groups of order PQ does require more advanced maths than we have built so far in the playlist on group theory. Okay, so we'll do that down the line. So for now, we'll just limit our attention to groups of order PQ where P does not divide Q minus 1. Again, here are your examples, the group of order 15 and groups of order 33. Okay, so the first thing to claim now is that if this is true, you can instantly say that the number of C log P subgroups is also equal to 1, and this is why it's so beautiful. It's got an incredibly simple subgroup structure, hence there's only going to be 4 subgroups. The trivial subgroup, the improper subgroup, 1 C log subgroup of size little p, and 1 C log subgroup of size little q. Okay? Right, so NP is going to equal 1, and therefore, if P, therefore, we'll call capital P the C log P subgroup of G, okay, we can therefore conclude that P is going to be the normal, it's going to be a normal subgroup in G, okay, the same argument as we employed up here, okay, if there's only one subgroup of this order, then conjugate it by any element of the group that you like, and it must just bring you back to this group. You can also say that it's going to be characteristic in G, but we'll just settle for normal. Okay, so P is a C log P subgroup, and it's going to be normal in G, provided that there is only one C log P subgroup. So how can we prove, therefore, that there will only be one C log P subgroup? So let's just have the proof of this then now. Okay, well again, it's a very simple argument, just using the third C log theorem. So I'll bring this up, and now we'll prove this. Okay, so the third Seelof theorem, again, what does the third Seelof theorem tell us? Well, it tells us that the number of Seelof P subgroups must divide the remaining portion of the order once you've got rid of the highest power that P appears to. Okay, that's going to be Q. So NP must divide Q. It must also be congruent to 1 modulo P, so it must be of the form 1 plus K times P here. Okay, again, where K is greater than or equal to 0. I claim that we can use these things along with this condition here to conclude that NP has to equal 1. Now, NP divides Q. What does that tell us? Well, Q is a prime number, so there's only two options for what NP can be equal to. Either it can be equal to 1 or it can be equal to Q. So all I have to prove is that NP is not equal to Q. So let's arrive at a contradiction. So let's say NP does equal to Q. Therefore, Q is equal to 1 plus Kp. And now, of course, what I can just do is I can say Kp is therefore equal to Q minus 1. But why is this a contradiction? Because we assumed that P did not divide Q minus 1. Okay, so that no multiple of P would equal Q minus 1. Okay, so if the primes were chosen such that that was the case, such as with the example, the order of the group is equal to 15, where this side would be 4 and P here would be 3, and therefore what are you going to make K equal? There is no option for you, basically. You cannot do it. Again, 33 has the same problem. You would not be able to find a solution to this, okay, where K has to be a natural number. Okay, so if we do have a group of order PQ where this is true, that P does not divide Q minus 1, then it is not possible to find a K such that this relation is true, that 1 plus Kp is equal to Q, and therefore NP is forced to be equal to 1, i.e. there is only one Seelof P subgroup, okay, and therefore only one subgroup of order P. And therefore we can complete our extremely simple chart now for these groups of order PQ where P does not divide Q. And I'll repeat that this is not true just for the arbitrary groups of order PQ, such as groups of order 6, 10, where we didn't have this additional requirement being true. But if we have that additional requirement being true, then this is our incredibly simple subgroup structure. We have the trivial subgroup, the improper subgroup, one subgroup of size P, which is normal, and one subgroup of size Q, which is normal, and those are both normal Seelof subgroups. Excellent. Right, now, here comes Theorem 3, and again, Theorem 3 is still going to be about these groups of order PQ where we have this additional requirement. So Theorem 3 here. Okay, so Theorem 3. So we've now got a finite group of order PQ. Once again, I'll just write all the assumptions. P is less than Q, and we're assuming that P does not divide Q minus 1. Then the now claim, the big claim now, is that actually I can say instantly what this group is isomorphic to. If this is the case, there is only one isomorphism class of groups that fulfills these criterions. Only one isomorphism class of groups of this order PQ where P does not divide Q minus 1. Okay, and that isomorphism class, of course, is going to be the cyclic group on the set of that order. Okay, so what I can conclude then is that G is isomorphic to the cyclic group on the set of order PQ, and you could call this CPQ if you prefer. Okay, the cyclic group on the set of order PQ. Now, of course, that group exists always. The cyclic group on the set of any order exists, and it will have order the same as the set on which it's acting. So that's a group that always exists for whatever order that you want. Okay, but the claim now is that that's the only group up to isomorphism that actually exists. Any other group of order PQ where P does not divide Q minus 1 is isomorphic to that. So this is very, very nice. It's just like groups of a prime order. There's only one isomorphism class of groups there for a prime order, and it's the same here where we have that the group has order P times Q where P does not divide Q minus 1. Now the proof of this is quite a tricky little argument when you see it for the first time, but it's a good argument. You'll learn a lot from it if you've never seen it before. Okay, so we will have a break here to have a little rest, and then in the next video we'll begin this argument for why that is actually the case.